Hello everyone, welcome to today's video. In this video, we are going to discuss about length extension attacks. Before we get into what length extension attack is, I'll start with a scenario and then tell you what exactly length extension attack is. So for our example, we are going to take two systems, system A and system B, who are interacting with each other and sending message. So system A is sending a message to system B. Now, they are sending a message over the network. And in case of any issue with the network, the message can get distorted and system B can receive incorrect message. Now, how exactly would the system B know if it has received the correct message or not? What they are going to do is, while sending the message to system B, system A is going to add a hash as well to that request. So the hash function can be an MD5, SHA-1, SHA-2, SHA-256 or 512. So system A will now send a message along with the hash of message to system B. Now what system B is going to do is, system B is going to take the message which it has received. It is going to regenerate the hash of that message and it is going to compare with the hash which was received. If the hash which was received matches the generated hash, then system B knows that the message which it has received was not distorted in between, and then it can consume the message. Now, in this, although system B is able to check for the integrity, there is no way for B to know if the message has actually been sent by the system A. Now, if there is an attacker sitting in between the network of A and B, it can receive the message sent by A, which is the message, and also the hash of the message. It can consume it and generate a new message, which is message dash and hash of message dash, and replace it with the original message and the hash and send it to B. The B will regenerate the hash and check it with the hash received, and it can over there, on the basis of this, it can say that the message which has been received is correct. However, since B does not know that the message has been sent by A, right now they are consuming it, but that can cause an issue. To get around this, what they can basically do is, they can have a shared secret between A and B. Both of them can have a shared secret. And while the system A is generating a request to be sent to system B, it will send the message as it is in the earlier request. However, while generating the hash, it is going to prefix the message with the secret which was shared between them. And since only system A and system B know the secret, only they will be able to generate the hash. Even if, let's say, there is a attacker sitting in between and it intercepts the message and the hash, it will still not be able to generate because the secret is only known by system A and system B. Over here, the system A and system B are using the hash as message authentication code, which is also known as a MAC. This authenticity check relies on an assumption that the correct hash will be generated by someone who knows the secret. Now, in this case, since only A and B know the secret, we are sure that the message to B was sent by A, and if message is sent by B to A, the system A knows that it was sent to B. On the basis of this assumption, we are able to work. But this is where the length extension attack comes into the picture. In length extension attack, an attacker can append extra information at the end of the original message and generate a valid hash without knowing the secret. So the scenario would look something like this, where a system A is sending the message and the hash of message. The attacker intercepts it, appends a message 2 at the end of message, and generates the hash of message plus message 2 using the secret. However, like we said, that length extension attack works without knowing the secret. So the hash will be generated without knowing the secret. For the length extension attack to take place, the length of the secret and the original message should be known. Even if the length of the secret is not known, you can brute force the length of the secret. This specifically happens when a Merkle-Damgard based hash function is used to generate the HMAC.
What is Merkle-Damgard function?
So let me get into the Merkle-Damgard function. So a Merkle-Damgard hash is basically, it works on a way where a message is divided into n blocks. So let's take an example and say that a block is of 8 bytes. So the message will be divided into n blocks of 8 bytes. In this example, it is divided into M1, M2, M3, and so on and so forth till Mn. And it is appended by the padding to complete that 8-byte block. Now, what happens is that the way it works is that an IV is passed on to the hash function, and it will be an internal hash function, and the first block of the message is passed on to it, and it generates a hash which is over here we are naming as H1. That H1 is again passed to the internal hashing function with the M2 message block, which generates the next hash, and so on and so forth. This process keeps on going on until we reach the last block of the message, which is Mn, and to that the Mn is passed to that internal hash function along with the hash generated in the last round of that block, which was hash of last message, hash of n minus 1, and then Hn is generated over here, which is passed to the padding block, which generates the final hash over here. So the way it works is that each hash is built on top of the hash of the last message block, and that is how the Merkle-Damgard hash function works. Now, in this specific case of a length extension attack, the way it will work is that the original message is of n blocks, M1, M2, so on and so forth till Mn. The new message will be of n blocks plus z blocks of the new message. So, and the hash generation for the message M will be taken care of the way we did it over here, and the final hash which was generated will be passed as an input to the internal hash function with the message block of the new message. So N1 will be passed over here along with the final hash, which was Hn plus 1 to the internal hash function. It will generate a new hash, and that hash function will be passed to the final block of the new message to generate the hash Hn plus 3. And after the padding it, a new final hash will be generated, which will be sent along with the older message and the newer message, which is the appended message. So it will.
मेरे को एक डाउट था, तो आई थिंक वी शुड आस्क इट राइट नाउ.
ओके, टेल मी.
पहले वाले डायग्राम पे जाओ. So I have one question on this diagram. So
Yeah.
This padding, isn't this padding appended on Mn, and like is this two-step process or a single-step process? Like Mn padded will be generated with the hash and you get the final hash, or is it a two-step process? Like Mn is done first and then padding is done as an extra step.
So you're right, absolutely right. So Mn also has a padding done, and when I say the final padding, it basically has a null character.
Okay, what is the use of that null character?
So null character is used to over here to specify if it was an end of the message. However, what can also happen is if your original message also has a null character, then there is no length listed in in any of the block. So it doesn't really know when is the end of the message. They just append it right now while generating the hash. A null character is appended at the end.
So even with this null character or the end delimiter sort of a thing present,
yes,
till the length extension attack can happen?
Yes, it can. So to make it simpler, to make it much more simpler, I can remove the padding over here. let's say I remove it over here, and in this case, the final hash will be the HN. HN will be the final hash over here. This is to make it simpler, although there is a null character padding added at the end. But for the simplification of this, I am just removing it so that it makes it easier for everyone to understand this. Does that answer your question, Sunny?
Yeah.
Okay. So after this happens, the system B will receive message plus new message and the new final hash along with it. And all of this is done without knowing the original secret. And the reason we need to know the length of the secret is because we have to divide the message n into number of blocks. We need to know the blocks till here. Only then we can generate new blocks over here.
So only if we know this information, this can happen.
So the thing is that while the system A is communicating to system B, they are already sending the message. So the original message is known to the attacker. The only thing which they do not know is the secret. And they only need to know the length of the secret. If they don't know the length of the secret, they can always brute force it, because it is not going to go beyond the length of the the length of the secret cannot go beyond the length of the block.
But what is the implication of it? How does knowing the length of the secret exactly help?
So knowing the length of the secret basically helps you determine from where you should start the block. That is where it helps you. So till now over here, you know the length of this whole thing, right? When you add a message over here, you need to know how much you need to pad and from where the block will be generated. So let's just say the secret plus message was coming out to be, say it is not proper 8-byte block. So it's not a multiple of 8 bytes. So let's just say it coming out to be 60 byte, the message plus the secret. So before we start appending the new message, we need to know how many bytes have to be added to complete the block. So they are going to add 4 more bytes to make it 64. That will complete the block, and that is when they are going to add the new message. So they need to know the filler bytes which have to be completed before they add the new message. And they cannot know that without knowing the length of the secret. They know the length of the message, but they do not know the length of the secret.
This is still not clear. Why?
Okay, let me take another step. When the hash is generated, hash is actually generated from secret plus message, right?
Correct.
Since we know that the hash only works on an 8-byte block.
Okay.
If this message plus secret is not coming out to be a multiple of 8 byte, it has to pad that to complete the 8 byte.
So that when you say
that
it
would
has
have been done already, right?
Sorry?
In the original hash, that would have been done, right?
That would have been done, exactly. But the thing
by the system. So by the algorithm, it would have been done like automatically with padding.
Okay, got it, got it. So that padding was used by the hash generating algorithm to generate the final hash.
Right.
When we need to generate it again, we still need to generate a complete.
So directly append it, we will basically mess up the 8-byte last.
Exactly. So when you are generating a new hash, you also have to update the message. When the message which you are sending to system B.
Right.
Over there, you need to add the padding in between. Else, while generating the secret, system B is not going to add the padding. It is going to use message plus new message. And this is where it is going to screw up, because while generating the hash, we know a padding was added to MN.
Right. So basically, you want while generating the algorithm, you want to mock the behavior of the previous message being hashed as well.
Exactly. Exactly. I have to complete that message. That is the reason we need to know the length.
Take it. This makes sense.
Okay.
And if we don't know the length, then basically even if we don't know, we can brute force it, because your secret will generally be not be too will not have high length. So you can always run a brute force attack.
Exactly. We can do that. Do you guys have any questions, or shall I move ahead?
Let's move ahead.
Okay.
Yes.
So now we have seen how a length extension attack works. Now, the real reason a length extension attack can happen is because of the incorrect usage of the hash function. So a hash should not be used to generate a MAC. A MAC is basically a message authentication code which adds an authenticity to the message sent. To circumvent this, what users should do is they should use the HMAC function with the right algorithm. So they can use the HMAC function with the MD5. If they want to generate a MD5 HMAC, they can use with MD5 by passing the secret and message separately. And HMAC function ensures that the hash generated out of this function is not susceptible to length extension attack.
How does HMAC help here?
So I'll give just a brief on how HMAC works. So HMAC basically works is using the secret. It generates two keys. I will call them inner secret, and one is an outer secret. And after generating these, what it basically does is it uses the inner key, comma message to generate a hash. Then it uses outer key, comma hash to generate the HMAC. That is how it works. It's just a rough idea on how it works.
Okay.
So if we are using hash function, like let's say hash of message plus secret instead of secret plus message,
Yes.
is it still possible to do the length extension attack?
In that case, it won't really be possible. So let me list down what exactly you are saying. So you are basically telling that you are going to generate a hash of message plus secret rather than the other way around. You will suffix the secret. So in this case, it won't be vulnerable to length extension attack. The reason for that is when you are going to generate a new message, system B will check using, and it won't generate the right hash. Because to have the length extension attack working, in length extension attack, like we discussed, you can only append to the original message. So original message in this case was message plus secret. So you can only append at the end of it. That means secret will now become part of the message which you are sending to B.
For length extension to work, your original message has your original system has to be secret plus message.
No, what I'm basically saying is if I have to run a length extension over here, since the original message is message plus secret, what we will have to do is we will have to generate new message as message plus secret plus new message. Then only it will work. But we do not know the value of secret, and that is the only reason we are protecting against it. But this is not the right way or the best practice to generate an HMAC.
So even in this case, since the secret is at the end,
yes,
there's no guarantee that the hash will ever match.
The hash won't match because we do not know the secret.
Yes, exactly.
That's the only reason we are secure against it, but this is not the right practice. The right way to generate an HMAC would be to use the HMAC function for that particular language.
Is the logic or algorithm for finding inner and outer secret known?
It is known.
And that is not vulnerable to.
It is not vulnerable because the thing is, over here you cannot append anything. It has to be the new hash. So it generates an H1 and then it generates an H2. So intermediary hash is generated over here and then a final hash is generated over here. So it is more like this.
Okay.
Now to do this, if we append something at the end of outer key, comma hash, then it is never going to result in the right way because they are going to generate a hash of inner key, comma message, which will generate some hash. And then they're going to use that hash to generate the final hash. So it is not going to match.
Okay. So the key thing over here is hash should not be used for MAC.
Exactly.
And are all the hashing algorithms vulnerable to this attack?
Not all the hashing function. The hashing function which are based off Mark Demgard algo are the ones which are vulnerable to this. Although they have made some changes towards that, what they are now doing is, along with padding, what they are appending, they are also appending the length of the message at the end to get around this vulnerability.
Is there an existing algorithm which is still susceptible, vulnerable to this?
You can do MD5 and SHA-1. They are vulnerable right now.
Okay.
And some hashes under the SHA-2 family are also vulnerable.
Cool. This was interesting.
Do you guys have any other question?
Okay.
Thank you, everyone. And please subscribe to our channel if you want to see more videos like this in future.